Okay, so today's video is going to be a little more sort of pure mathy. The topic is vector spaces. Now, I said before that we had sort of a working definition for a vector. That was, a vector is an n-dimensional tuple. Yeah, okay, fair enough. Here's the more rigorous definition. A vector is an element of a vector space. That seems a little weird. Well, okay, let's go with the geometric version, 2D and 3D vectors that we're used to, and examine sort of what a vector space means. So let's say I have a vector, it's two-dimensional, so I can just plot it in the paper. That's V. And then I look at all the space that can be spanned by that vector. Well, this means we can stretch it out as far as we want, and bring it back to the origin and stretch it with a negative component. So there we have it there. Let's call this our origin, because 0 times the vector will be through the origin, and this is an infinite line. So what we have is we have basis vector V, and then we have if I multiply that, that's within V. So I'll have this space of the infinite line is V. And then if I have, 0 is within V, I can add two vectors and the resultant is within V, provided we started with vectors in V. And that's it. That's a 2D vector space is, well, what is space in 2D? It's an infinite line. Let's look at a 3D vector space. This is an example of a 3D vector space with, well, it's actually a 2D vector space, isn't it? Now I'm getting a little weird because it has two vectors, two basis vectors. Okay. So I'm muddling up my definitions a little bit, but if I take V and I stretch it in any direction, that's fine. I'm still within the vector space. If I take U and I multiply it, so I stretch it in any direction, I'm still within the vector space. And if I take a summation of an element from U plus an element from V, that gives me a point within the plane. So the span of this is any linear combination of the two basis vectors. It defines a 3D plane. Now, like I said, this is a little more pure mathy. So I think the idea of stretching out lines to make infinite lines and using lines to make infinite planes is useful, but it's a little more abstract today. So onto the definition, the actual definition of a vector space. We have two structures. We have a set V and a field F. Most commonly, that field F will be real numbers. Could be complex, I guess. Why not? But it's a field. And then we have two operations, summation and multiplication. And what we have is the summation operates on elements of V. So we have the Cartesian product. So it takes two vectors and stays within the vector field, the vector space, the vector set. And the multiplication is scalar multiplication. So it operates on an element of the field and an element of the vector set, and returns a result which is within the vector set. So the way I would think about it is a vector space is any set that when you take two vectors, two elements, add them together, you stay within the set. And if you multiply an element of the set by a field element, then you stay within the set. If we think about that, that definition works for 2D and 3D vectors. It works for n-dimensional vectors. It also works for things that you wouldn't think of as vectors. So continuous functions, for instance. If I add two continuous functions, my result is a continuous function. If I multiply a continuous function by a scalar, then my result is still a continuous function. So that's what I mean when I say things start to get more abstract. Now, to give the formal definition, this is sort of I'm sort of spiraling into the formal definition. So what we have is that these operations are both closed, so the result will always be within the vector set. Addition is associative, so if I have three vectors, u, v, and w, it shouldn't matter how I add them up. I should be able to add v and w first, or u and v first. And similarly, it is commutative, so the order that I add things doesn't matter. I think of commutative as literally to commute. So if I take the u direction and then the v direction, that's the same as taking the v direction and then the u direction. If you think of adding vectors as like translating through points. Okay, we should have an identity element. So we should say there exists, let's call it, I'm going to call it 0. Okay, so there exists an element 0 within the vector space such that 0 plus v returns v for all v in the vector space. So commonly the 0 vector will literally just be the 0 vector, or if we come up with some kooky version of our vector elements, then it would be something else, but it has this property. Then we have an inverse for addition. So we say for every element of our vector space, there exists an additive inverse such that when I add these together, I produce the additive identity. And it's important to think of these not just as negative v and 0. I know I definitely wrote that. It's very tempting to think about them that way. But remember, we could have some weird abstract math system where these are not the intuitive idea of negative v and 0. So we want to keep it as general as possible. Then we have some properties. So for, we'll say A and B in our field, then grouping things together shouldn't matter. So if I go B, V first, or A, B first, that should be the same thing. Then we will have an identity element for scalar multiplication. So we'll say there exists, and again, it's commonly called 1, but it's really the identity. So there exists an element in our field such that if I multiply that with the vector, it keeps the same vector for all vector elements. And then we have, I'm kind of running out of paper here, but we have the distributive law as well. So we go scalar times u plus v equals scalar times u plus scalar times v. And then similarly, if I add up first, then we have AV plus BV. And this is the formal definition of a vector space. But again, in practice, the way I like to think about it is I like to think about vectors are basically any sorts of elements from a set that when I add them together, I stay in the set. When I multiply them with numbers, the result stays in the set. Anyway, that was a bit abstract, but yeah, that's the definition of a vector space. Anyway, hope you enjoyed that, and I'll see you again soon. Bye.